So this video is about universal gravitation, which is simply the idea that all matter in the universe pulls on all other matter in the universe. So any two objects, it does not have to be a planet to be noticed, to exist, but it really has to be a big object to notice it. But any object, this marker and this plastic cube, for example, there is a force of attraction between them. Wait for it, they'll snap together. No, they're not. You're not going to see that because it's a very, very weak force. In order to notice it, one of the objects at least needs to be a very large object, like the Earth, which is why we notice it when I drop something, because they do snap together. This object, the cube and the Earth, did pull together. It's a large enough force to actually be noticed. But in this case, it's a very, very tiny force. But the universal nature of this is given by a simple, well, relatively simple equation. And that is the force of gravity between any two objects. Well, it depends on the mass of the two objects. So m1 times m2. So for example, if you have some mass 1 and some mass 2, the two masses together, multiplied together, are important. The bigger the mass, the bigger the force of gravity. Divided by the distance between them squared. Now it's important to note that that distance is actually from their centers. And normally, what's a big deal, center edge, but if you're talking about something like a planet, and you ask somebody how far are you, what's your R value, for example, when you are standing on the Earth, somebody might say 0 because I'm touching the Earth. But the truth is, if this is the Earth, your distance from the center of the Earth to you, to your center, is the radius of the Earth in this case. So keep that in mind, is that it's to the centers of the object. Now, I mentioned a second ago that gravity is an extremely weak force. There's a constant that goes with this equation that is not a very big number, capital G. And capital G has a value of 6.67 times 10 to the negative 11th. Now the units, we can figure this out. We want newtons, right? This is going to be a force. So I want newtons, but in order to do that, I would have to first, let's see, I would have to get rid of kilogram squared. Kilogram times a kilogram. So, and they're in the top, so I'm going to put Newton over kilogram squared, and in the top I need to get rid of meters squared, because this is going to be a meter times a meter when I square. So these would be the official units. But gravity is a very weak force. This number is our clue that it's a very weak force. Okay, so really, if you can, the issue with this is usually the algebra, and one other possibility. And I'll throw this one at you, but it's really not a lack of understanding of gravity. But let's try this. So we have this situation. A large mass, big M1, and a small mass, M2, separated by this distance off. So which of the masses experiences the larger force? Now, you've been in physics hopefully long enough to realize that that's a loaded question. And in fact, if a physics teacher asks you which one's bigger, the chances are they're probably the same, and in which case they are. And the reason they're the same, and the reason I want you to be very wary of this question, is a couple things you need to think of. First of all, Newton's third law. This is not really a gravity question, this is a Newton's third law question. Big mass pulls on little mass to the left. Then we reverse it. Little mass pulls on big mass to the right. Those two forces, Newton's third law, have to be the same. The other clue that we have to that is this, is when we write that formula for the force of gravity, and we say, all right, big G, in this case, big M1, little m2, divided by the distance between them squared, is this equation for mass 1? Or is it for mass 2? It doesn't really say it's for one or the other. It's because it's for both. So the force that this experiences to the right is the same as the force that this experiences to the left. I pull on, if you're thinking about a human being in the Earth, I pull on the Earth, with the same force that the Earth pulls on me. I accelerate when given the opportunity, and you don't notice the Earth's acceleration because of Newton's second law, F equals ma. And the bigger the mass, the less acceleration you're going to see. So that's one situation, one thing about this that I need you to be aware of, is that be careful of, on which one, you're tempted to say, oh, the force is bigger on this one, but no, the force is the same on both of them. Another situation you're going to run across, and this is where the algebra becomes an issue. It's a little bit wordy. I recognize that, so you might want to pause and read it through. But the idea is this. You have two objects, both with the same mass, m initially, and they're separated by a distance, we'll call it capital D. And they experience a gravitational force that we call F1. Fine. Then they mess with the masses and the distances. They say one of these masses is tripled, and the other mass is doubled. And they're moved to a new distance apart that is 3 times larger than it was before. And we'll call, when they're set up like that, we'll call that force F2. And they want you to find F2 in terms of F1. In other words, when you're done, you're going to write F2 equals some number that we have to find times F1. In other words, is F2, should it be half of F1? Or is it 3 times F1? Or is it 7/5 of F1? Whatever, there's a number here that we need to find. And I'm going to run through with you now the technique we use to find that, how that works. So, let's do it right here. We have two situations. Situation 1 was both objects were m, and they were separated by a distance of d, and so the force of gravity between them, we'll call F1, was capital G m times m over d squared. No big deal. Check. Now, we look at situation 2. We triple one of the masses, so we'll call this 3m, and we double the other, and we move them 3 times this distance apart. So roughly speaking, maybe out here. And this one's 2m. And they're now 3 times that distance apart. Okay, what would be the force 2 between them now? Well, plug everything in. Big G, 3m times 2m over, this is the crucial part. This is the part that you'll probably make a mistake on if you're not careful. 3d squared. The entire thing gets squared. And I'd like to point something out back here real quick. We can take one more step here and write this. That's big G times m squared over d squared. Since the masses m is the same, I can write it like this. That's a quick jump back. So here, what your goal is when you're doing these problems is to get this, just rework it carefully, and we'll see how, to look like some number, I'm going to write it over here, some number times g m2 over d squared. Why do I need to get, why is this important? Well, if you look over here, that is F1. So I want to move things around legally, mathematically, so that I get a number out here and this, which is F1, by itself. So let's take a second and let's multiply some things out and so forth. For example, capital G stays. 3 times 2 is 6, so I have 6m squared over this, when I square it, is 3d times 3d, that's 9d squared. And I'm going to just move anything that isn't this, this, or this over to the left. So the 6 and the 9, it doesn't matter what order you multiply them, right? The 6 can go in front. Right? 6 times g times m squared is the same as g times 6 times m squared. The order doesn't matter. So F2 can be written as 6/9 times g times m squared over d squared. So I just move the numbers out and look what I have here. That's just F1. So F2 is 6/9. We can reduce that. That's 2/3 of F1, because this right here is simply F1. So the technique is to set up both ways and then rework the second way so that whatever the constants stick out here, move them out to the side so that whatever you have here is the same as this. And that's the little trick we use for those. So those are the two types of issues that you might run across when it comes to universal gravitation. Keep in mind it's an extremely weak force, and that the force on both is the same, just opposite direction, and that's a consequence of Newton's third law. We'll get to gravitational fields in the next video.